Okay, so I was asked to come here and talk a little bit about NOX, POX, and kind of controllers more generally. I'm going to start out with a little bit of history, and then get to kind of the point of this, which is two sets of lessons of things I've learned working on controllers. The first two are two kind of small ones. They're kind of intertangled. They might be kind of NOX and POX specific. The second one is kind of a significantly more significant lesson, which has to do kind of with writing controllers in general. If I've got some time, I'd then like to talk a little bit about some kind of ongoing work in the NOX-POX ecosphere, and I think that'll take us pretty much to 25 minutes. So NOX and POX, the primary collaborators, are listed here. These are the current collaborators. You can see a lot of us are at ICSI, which is the International Computer Science Institute. A number of us are also at UC Berkeley. Amin is at the University of Toronto. NOX and POX. POX has been up on GitHub for about a month. The new version of NOX will be going up on GitHub this week. So also, anybody with a GitHub account is now a collaborator on NOX and POX. We've had certainly input from outside groups in the past, but hopefully this is really going to streamline that. So NOX was pretty much the first SDN controller. It was developed at the same time that OpenFlow was being developed. A number of people were active in both projects. There was quite a bit of back and forth. There was a synergistic relationship there. It was originally developed at Nicira to be the basis of SDN products of Nicira's. In 2008, they released it as open source under the GPL. That's about when I became involved with NOX. Since that time, it's been used really extensively in SDN research. And while Nicira has gone on to do other things with SDN, NOX has now become maintained by the community. The view of NOX from orbit is that it runs on Linux. As far as I know, nobody has ever actually got it to build under BSD or Mac OS or Windows. The first two are probably doable with some effort. The latter one probably with significantly more effort. It utilizes cooperative multi-threading. It has a component system for kind of segmenting your application functionality. It has an event-based programming model. It's got a library for doing packet dissection and packet composition. And then it's got a number of kind of sample applications for doing, for example, reactive routing, topology discovery, host tracking, and various other things. So in my time working with NOX, we've learned a couple lessons here. Deployability matters, and language choice matters. So the first one is based on this observation that NOX is difficult to deploy. Since we're targeting research these days, it's generally deployed as source code. And the build is actually fairly complex, and there are quite a few external dependencies. This is not an ideal situation when you have researchers as your primary audience. This means you constantly have kind of an influx of new users. And your experienced users are also researchers, meaning they typically would rather be working on their research than helping new users come up to speed or trying to iron out the build process. The second observation has to do with the fact that NOX is both written in C++ and Python and can be extended in C++ and Python. The expectation here, I think, by Nicira was that Python was going to be used sort of as a configuration language and as glue to bind together sort of more significant C++ components. But in actuality, for researchers, this doesn't really seem to be the case. Researchers, in general, want to write in Python because it's quick and easy to do. And while we've also seen significant applications written in C++, more probably written in Python, but while we've seen some written in C++, we've seen practically none that were written in both C++ and in Python. So a result here is that the Python API isn't great for writing complete applications. It wasn't really meant to be. The OpenFlow interface is kind of more sticky than you might want. Various things that you would want to work in Python, for example, multi-threading, just don't work. And maintaining this API in Python is kind of, well, it's more work than one might want. And while I think we've been pretty good about responding to user requests to come up to feature parity in C++, it is something that we do as on kind of an on-demand basis, and that hasn't really worked out great. And for people who want to use C++, this is all unnecessary complexity. You have control paths that go from C++ to Python to back to C++, and this is just kind of confusing, and it doesn't actually buy you anything if you want to be writing in C++ anyway. So trying to extract some lessons from that, the first was that deployability matters to us, and we need to pick our dependencies really carefully. A fair amount of the traffic on the NOX dev mailing list is really just people having trouble getting NOX to build and even just getting dependencies satisfied, especially if they're not using the distributions of Linux that we use when we develop it. A second one is that we should pick a language, because maintaining and integrating two languages takes quite a bit of effort, and as it turns out, nobody actually cares. So to confront this, the first thing we've done is remove Python support from NOX. The new version of NOX no longer supports Python. This immediately simplifies the code, makes it a lot more approachable if you want to be writing C++ controllers, because you no longer have these control paths that go C++, Python, back to C++. It also removes quite a few dependencies and quite a few steps from the build process, which makes it just easier to get built. This also has allowed us to change the threading model. As I said, NOX previously used a cooperative threading model. The new one no longer does, and this has actually gotten some pretty interesting performance impact. And basically, this all just goes to making NOX a better platform for people who want to write controllers in C++. So the other thing we did, since a lot of us really like using Python to write controllers, including us, we built a new platform purely in Python. We did want to take to heart, these lessons I was talking about, for example, picking our dependencies carefully. We also wanted to take things that we liked from NOX, for example, the packet library, the GUI, the component system, all of these are either inspired by NOX or taken directly from NOX. But we also wanted to spread things out a little bit, and by that, I mean we wanted to support not just Linux, but also Mac OS and Windows, and to kind of make this a little bit more accessible. Lastly, we want to use this as the basis for all of our research on SDN moving forward. So our goal here was to write a platform for writing controllers for research. A non-goal here was performance. A little side note on that, what performance means when you're talking about a controller, or what people generally are talking about when they're talking about performance in a controller, is kind of limited to cases of strictly reactive controllers, which isn't really where our interest has been in our own research. Moreover, if that is something that you're interested in, a controller like NOX has much better performance measured by that specific metric, so we actually think the two are sort of complementary. So looking at POX, like I said, we want to pick our dependencies really carefully. So the first one we chose was Python 2.7. Python 2.7 is supposed to be the last version of Python 2, which means we think it'll probably have a pretty good lifetime here. It's the default Python on Mac OS, on Ubuntu, on the next version of Debian. And it's got lots of nice new stuff, including stuff that's kind of been backported from Python 3. And perhaps almost as significantly, it's supported by PyPy. And PyPy, if you're not familiar, is an alternative Python runtime. It has a JIT compiler, and the performance is generally like 4 to 5 times what you'd see with the default Python interpreter. So if we can get 4 or 5 times performance increase for free, then we'll take it. One of the other nice things about PyPy is that it's extremely easy to deploy. You can really take a zip or a tarball from the PyPy website, decompress it into POX's directory, and POX will run with it. So you can easily make bundleable versions of POX. So that's actually it. That's the Python 2.7 is the only requirement for running POX. OK, so on to the bigger lesson, appropriately titled Thinking Big. So we're going to motivate this with perhaps the simplest possible SDN application. Say you've got a network, and it's got some endpoints associated with it, probably like hosts. What you'd like to do is, for every pair of hosts, you want to install some optimal paths. So how do you do that? Well, here's a little bit of pseudocode, which, as you can see, first thing you do is clear the flow tables and the switches. Then, for each pair of endpoints, you calculate some path. To calculate a path, you basically pick some best path, maybe using like Dijkstra's algorithm. You install that paths, and then you keep track of which paths you've installed. Now, if you were to lose a switch, you'd like this to still work, which means you need to react to that. So you'd write some other function here, handle switch down, which basically looks through the paths that you've installed, figures out which ones use that switch, and then calculates new paths to replace it. If that switch comes back up, you're then going to want to confront that situation too, because maybe now there's a new optimal path. So you write some other function to handle the case where a switch comes back, where you look for new optimal paths. There's other cases that you might want to consider here too. For example, if an endpoint is moved, for example, if it's a VM and the VM is migrated. So you write another handler to confront that situation. Now I've kind of run out of space here, but then you still need to think about when links go up and down, and maybe when you add or when you remove endpoints, and then probably some other stuff that I'm forgetting. So taking a step back, what have we been doing here? We've been taking events, we've been writing these event handlers, which then send some commands to a switch. Thinking a little bit more abstractly, what you're doing is you're writing a function which maps some change in the network state to some change in configuration that you'd like to see. This is a pretty natural way to write your control logic, and it kind of falls naturally out of OpenFlow. OpenFlow messages are largely deltas. A switch to a controller message is generally communicating some change in network state. The commands that you send from the controller to the switch generally communicate some desired change in configuration. Most examples of SDN code work pretty much like this. But as things get more complicated, it's really hard to get this right. Why is that true? Well, first of all, some of the state is stored on switches. That turns this into a distributed systems problem. As far as the controller is concerned, some of that state is at the end of some piece of wire somewhere. If that was really easy to do, none of us would be here. So first of all, you've got problems with reliability, communicating these deltas. Additionally, it's really easy to make these subtle mistakes, these subtle bugs, where you assume some ordering which actually isn't true or isn't always true. And these errors, since they're based on deltas, are cumulative. If you miss a message from a switch, then your state internally becomes off, and it's hard to tell when you'll reconverge on a true state. Same thing, when you send a message to a switch, if that message doesn't get there, then any assumption you have about the state of the switch from that point forward is going to be wrong. You also have state that's held in the controller. Even in this kind of trivial example I gave, there's two kinds of controller state here. Some is held by the platform. To compute those best paths, we sort of implicitly assumed that the platform had knowledge about what the topology was. And then we also have kind of application-specific information. That was the list of paths that we'd installed already. So you're already, even in this trivial example, you're juggling 3 different kinds of state, which have different properties and kind of different owners. On top of all that, the code was kind of complex. I filled up a complete slide with the code, and that wasn't even complete. Each different type of event required a different little algorithm to kind of deal with that event. So the alternative is, rather than think about a link down event leading to some change in configuration, or a switch up event leading to some change in configuration, or any other change of state leading to a change of configuration, you just think about writing a single function which maps the entire network state to an entire network configuration. So this line of thinking falls naturally kind of out of the Shanker-Casado component view, which you heard about earlier, which says that a control program takes a view of global network state and produces configuration for each network device. So said another way, every time the network state changes, you recompute the entire network configuration. And so just to be clear here, I'm not claiming to have invented this. This really is the work of Martin Casado, Teemu Koponen, and Scott Shanker. So what this looks like in practice, going back to some pseudocode, it looks kind of like the pseudocode that we started with before, where to update the state for each pair of endpoints, you compute some best path, and then you install it in the switches. The difference is that this is it. This is the entire code now. So the implications of this are obviously you have a lot less control logic. You have a single deterministic algorithm which determines how you transform state to configuration. There's no chance of having cumulative errors in this piece of code because it has no state. Of course, the platform has gotten more complex. Since OpenFlow still communicates in terms of these deltas, the platform needs to take care of building a local model of the state and maintaining that. And then when you make changes in configuration, it needs to compute the deltas between your old configuration and your new configuration and just send those along. So obviously, you still have this problem of cumulative errors here, too. However, now, since this is the platform's problem, you only have to do it once. And it's easier to do because you don't have application-specific logic kind of scattered in with it. It also becomes easier to reason about your control logic because the input to the control logic is now this like temporal spread of events. It's now just a single view of the network state. The downside, of course, is that it may involve more computation because every time there's a change in state, you do recompute the entire configuration. So I'd also like to talk really briefly about some ongoing work. We have a number of things, though this one I thought was particularly interesting. And that's this idea of troubleshooting. You've got some control logic, and the control logic computes your configuration. But you add some various other things to the platform. For example, like I was saying, computing the state and configuration deltas. Perhaps distribution becomes part of your platform. Slicing becomes part of your platform. There are other various things that you may add to your platform. This is adding kind of distance to the metal between the control logic that you write and the actual configuration of the network. And so to some degree, it becomes harder to reason about. Additionally, you introduce the possibility of having bugs within that platform somewhere, where your eventual configuration may have there may be a mismatch between what you declared you wanted with the control logic and what you got with the configuration of the network. The observation here is that SDN is all about software, and all software needs a debugger. So the approach that's taken here is to instrument the platform and then be able to check for correspondence between each layer. So the code for that the early code for that is available on GitHub now. Along with that, there's code for NOX Classic, which is what we're calling the original NOX that has C++ and Python support. There's the new NOX, which will be available this week, which is just the C++ version of NOX. POX is up on GitHub now. We're continually adding stuff to that. The SDN debugger is also up on GitHub, and you can find all of this starting at noxrepo.org. So that's actually all I have. I guess I finished up a little bit early. Any quick questions? Yeah. Sure. In the application. So I'd say, let's see, I think there's two reasons. So one is really that by having this clean separation, right, and like I said, that becomes part of the platform, meaning it's reusable, like in terms of maintaining the state. You only need to get that right once, meaning every new application you write and every change you make to your application, you're not running the risk of reintroducing some new subtle bug to maintaining the synchronization between the switches and your own view of the state. Once you solve that problem, theoretically, it should be solved. The other one is just that the problem gets sort of simpler. Just from experience, I can tell you that when you're actually trying to build an application and you're trying to, at the same time, confront both problems, that is, implementing your own kind of incremental algorithm, as well as trying to make sure that you're synchronizing with the state of the switches, it's like a combinatoric problem. It gets much more difficult. And in fact, just slicing it into separate pieces and solving them independently is just easier in practice. Yeah?
By abstracting the problem, instead of based on mapping deltas to deltas, we've got the entire state to configuration. Is there a reference where one can see the mathematical complexity that's introduced by, your final point was this is a lot more complex in terms of computation, level computation. How does this scale with regard to number of hosts, guests on hosts, devices, so on and so forth?
Sure. So I don't have any, I don't have any backup slides or anything that confront that situation. One thing I can say is that there are cases where to recompute even a partial state, you actually need to do a significant amount of work anyway. Another thing I can say is that we think that this is a problem you can distribute. In fact, that there are ways to distribute this problem that are not even particularly difficult. and get decent results. You still end up computing a lot, but just by dividing up your computation in clever ways, it ends up not being a total killer. We're actually working on a paper for that, about our approach to that right now.
Is it just dividing the computation, or is it also dividing maybe localize the view of the network so that different controllers spread around the network can look at certain aspects of the network?
Right. So that's actually kind of the key to it, and figuring out kind of a general way to divide up your view of the network to let you break down the problem is actually the approach that we're more interested in. In terms of like trying to break down individual computation, I mean, that's just distributed systems and distributed algorithms, which, add their own whole level of complexity. So actually, we'd rather solve it by dividing up kind of the high-level workloads rather than, the actual algorithms. So that's actually what we're focused on.
And when is the paper due?
The paper is due for OSDI, which is 2 or 3 weeks. And so we'll be putting something out about it after that.
Cool.
I think that's probably about all my time. So we'll have a shared question and answer later. And if you have any additional questions, we can go over it then.